This is lesson 4.3, and we're going to talk about the intersection of a line and a plane. So let's just backtrack for a second. Unit 3 was all focused on lines. And so when we focused on lines, we were talking about how two lines interact with each other in 2D and 3D space. Now we're going to be talking about lines interacting with planes. So we're amalgamating Unit 3 and Unit 4. So we talked about lines and lines. Now we're talking about lines and planes. Obviously, in the future, we're going to be talking about planes and planes, which is mind blown. Okay, so don't worry about that yet. We're going to just do a quick review of lines and lines, and then we're going to get into lines and planes, and we'll worry about planes and planes later. Okay, so let's do a quick review. In 2D space, you have three cases. And the first case is where you have two lines, they never touch, no points of intersection because they're parallel and distinct. Case number 2 is where you have two lines, they touch all the time, and so they have infinite number of points of intersection because they're parallel and coincident. The third case is where you have them touching once, so one point of intersection, because they're not parallel to each other. Okay, now in 3D space, you have the same thing. Case 1, 2, and 3 are exactly the same, but we do have an additional fourth case. These are skew lines, and so they're not parallel, but they also don't intersect. And that's because you have that third dimension, the z-axis. So in case, case 3, it kind of looks like it's in two dimensions where they lie right on top of each other, and so they cross that one time. But in case 4, you can extend the blue line and you can extend the red line, but because one is floating above the other one, they actually will never touch each other, and so there's no points of intersection. Okay, so that was all lines and lines really quickly. I want you to pause the video and think about how a line and a plane can interact with each other. So try to visualize what are the different cases that you could possibly have. I'm going to move on. You can pause the video. Don't cheat. Okay, so here are the three different ways that a line and plane can interact with each other. So I got plane 1, and then I'll draw in line 2. So in this case, the first case, I'll just draw, why, I don't even know why I drew that. That's weird. There we go. Line 2. In case number 1, I drew them both parallel but distinct from each other. Okay, so I want to make it very clear that you can change up the angle of this line if you want to, and you're going to be like, well, but then they're going to touch each other eventually. They actually won't if you can imagine that all of these purple lines are on a plane that are parallel to the plane below. So think of a piece of paper that's floating above another piece of paper. If on the top piece of paper I draw a bunch of lines, they will never intersect with the paper below it if both of those pieces of paper are parallel to each other. Okay, so this is what I mean by 3D space. That can be a possible option. Okay, now in the second case, it's probably something that you thought of, where you have a line and it will touch your plane once because it'll continue through. Okay, so it like pierces through that other plane, and so your point of intersection is 1, and you would have to find that point right there. Now the last one is where they're parallel and coincident, and that's where the line lies right on the plane. Okay, so remember how we had said it really doesn't matter what the angle is. All of those are technically parallel and they touch the plane infinite number of times because they lie right on top of the plane. So these are the three cases, and obviously the types of questions you'll see are, here's an equation of a line, here's an equation of a plane. Tell me how many points of intersection they are. And if you can find that they have a point of intersection, what is it? Right? So those are the types of questions you'll get. And that means that we'll need some tools to help us to eliminate which case we're talking about so that we can narrow into our own case. Okay, so here are some tools that we might be able to use. And let me just explain. So we got plane right here and plane right here, and let's draw in our lines. If I have a line that is parallel to a plane, what you'll start to see is that the direction vector, so there is a direction vector that's associated with the line, that direction vector interacts with the plane's normal in a certain way. And so the plane has a normal vector, which is obviously perpendicular to the plane. Now, if I continue this up as a normal vector, notice that if this is perpendicular to the plane, it's got to be also perpendicular to the line, right? And so the normal vector and the direction vector, the pink and the green, they're both perpendicular to each other only if the purple line and the orange plane are parallel. Okay, so what I can do is I can prove that the line and the plane are parallel if I do the dot product of the normal and the line's direction vector, and it equals to 0. This is a tool that I can use where I can then say, okay, if this is actually the case, then you have a parallel line and plane. So I can prove that these two are okay, and I can eliminate this one if the dot product is equal to 0. All right. Let's take a look at the other one. Here we have the opposite, where if I have, say, a normal vector like this to the plane, and I also have the direction vector. Why did I do that? Okay, so the direction vector is parallel to the normal vector, then that must mean that my line goes through at one point. Okay, so remember the direction vector is on the line. If the direction vector and the normal vector, so the pink and the green, are parallel to each other, and the pink is perpendicular to the orange plane, that must mean that the line is also perpendicular. So that is something else that you can use by saying, okay, if the normal and the direction vector are scalar multiples, they must be parallel, which means that the line and the plane are perpendicular. I know, so many parallel and perpendiculars, I'm sorry. To be honest, I mainly use the first tool, the one on the left, a lot more. So as long as you understand that one, I think we're good. Let's take a look at some examples. So when I'm referring to a plane and a line, I'll try to use different colors so that you can follow. But it actually makes it a lot easier to do these intersections when the plane is in the form of a scalar Cartesian form and the line is actually in parametrics. All right, so let's take a look at example number 1. Determine the intersection. So obviously they're asking, is it 0 intersection, 1 intersection? And if it is 1 intersection, what is it? What is the point of intersection? And then is it infinite points of intersection? Okay, so let's take a look at the line. It looks like the line is, oh yay, in parametrics, obviously. Awesome. And then the plane is in scalar, which is great as well. Okay, so here we have our plane. It's in scalar. And we have our line, which is fantastic because it's in parametric. And so let's just make sure that we eliminate that case number 2. Let's see if the direction vector for the line and the normal vector for the plane are actually perpendicular to each other. So we'll do the dot product, and you guys should know by now how to see the direction vector right away. It's the numbers in front of the t's. And so in front of our parametric, that's going to be our direction vector. Also with the scalar form, you should know that all of the coefficients in front of your x, y, and z, that's going to be your normal vector. Okay, now when we dot those, if it equals to 0, it's case number 1 or case number 3 because both of those require the line and plane to be parallel. So it looks like the dot product is 19, which means that it's not equal to 0, and on the right-hand side, I said that they're not parallel, which means that you have a case of a plane and a line which pierces through, and you have 1 point of intersection. Okay, now the thing is, we can't just stop there. You wouldn't get that many marks on a test if you had said, okay, 1 point of intersection, and you're done. You want to know what that point of intersection is. And so if we've ever done a point of intersection between, say, like two lines before, like grade 10 stuff, when we tried to find the point of intersection, we did substitution elimination, right? And so we can actually do that here too. You have an x, a y, and a z. This guy has an x, y, and z. That point of intersection is your x, y, and z where they both have the same number. And so you can do substitution. Okay, so try to follow with the equations. I'm just going to scroll down now. Okay, so we're going to sub the x, y, and z of line 1 into the x, y, and z of plane 2. Okay, so you'll notice that you're left with a lot of t's and no other letters. So intuitively, even though we don't really know what to do, we will start to work with it. And so you'll start to expand and you'll start to simplify. When you simplify, you actually solve for a t value and we got -2. So what does that actually mean? Well, let me just show you. I'm sorry to keep scrolling up and down. This t value, when it's -2, will give you certain x, y, and z on the line 1. That x, y, and z are going to match the x, y, and z for the plane 2. So what we can do is we can find the point of intersection by subbing in -2 into the blue t's and then figuring out what the green x, y, and z is. Okay, now we're just going to do that, but we also want to make sure that we check with the plane 2 as well. Okay, so I got t as -2. I subbed it into each of the component equations, so the x, y, and z equations of line 1, and I got a new x, y, and z. So this is the point of intersection of the line and the plane. Now you could have made a mistake somewhere before, and so what you also want to do is maybe do like a little check. Check to make sure this x, y, and z fit nicely onto your plane as well. And so sub them into your x, y, and z of your plane equation and see if it balances on both sides. If it does, it means that you got your answer correct and that your point is actually -1, 2, and sorry, did I say -1? +1, 2, and -1. So this was an example of a case of number 2, right? We will see different cases later on, but before we do, I want to show you something. So there are actually 3 different scenarios. When we did the substitution and elimination and we actually solved for t, we got t as -2, like this is what we got just a second ago. If you ever get t as an actual value, like a number, okay, so t is, I don't know, 0 or some other number, that means that you're going to get a point of intersection because t actually exists as a number. Whereas in case 2, if you ever get 0t equals a number like something like this, that doesn't make sense because 0t is 0 and 0 can't equal to 3. And so if this is a case where it doesn't really make sense, then that is the case of having a line that is then parallel and distinct from your plane. Okay, so like there are no solutions. This is like no solutions. So that's similar to this one, which is no points of intersections, no solutions, right? And let's just recall this guy is where you have a line that goes through. Okay, so 1 point of intersection, this will actually give you like 1 answer. Now this guy right here, if you ever get 0t equals to 0, well, t could be anything. Like you can sub any number into t, and when you take 0 and you multiply t, it's still going to be 0, no matter what t is. So t has infinite number of solutions. And that would be the case where you have your plane and the line lies on top of it. So this one is infinite points of intersection. So really all we have to do in any of these cases, do the dot product, see if your line and plane are parallel, and then just check out the t. And if the t value is any of these three cases, then you've already narrowed down which of the three cases the intersection is. Okay, so let's try again. Example number 2, determine the type of intersection between a line, so I can tell that that's a line because you have one parameter, your t, and you have one direction vector behind it. And your plane, and I know that's a plane because you have two parameters, m and n, and two direction vectors behind them. Okay, so I'm going to underline these in the colors that I like. So that's this one, and this one is this one. Okay, so which of the three cases is it? Is it one point of intersection, 0, or infinite? All right, those are not in the forms that I like them in. Remember, we want the line to be in parametric, and so I'm just going to change this to parametric form, but I'm not going to go through that. You can watch another video on that. Okay, and then I also want to change this the plane to a scalar form. So that was always a little bit difficult. We have two direction vectors, but remember, for a scalar form, you need a normal. And so I'm going to cross those two in order to figure out the normal vector. And I got something that I could pull out, maybe a nice like common factor and make it even simplified more. And so that 1, 1, 1 is my A, B, and C that goes in front of my scalar form. Okay, and to complete it, because I need my D, I don't have a D, I will then use a point that's on the plane itself, and I'll sub it into the X, Y, and Z. Okay, so you still have your A, B, and your C in front of that, and you're just going to solve for your D value. So your D value you sub back in, and you get your scalar form for your plane. Okay, so that's what I wanted. Now that I have my parametrics in purple and I have my scalar in orange, I want to find the intersection. So we had said substitution, right? So you have your X, Y, and Z equations that you can then sub into your X, Y, and Z and solve for your T. Sometimes your teacher will ask you to also make sure that, you don't have to do this each time, because if you figure out your t value, you can then tell me right away which of the three cases you have. But if your teacher asks you to do like a full analysis, you might also have to show the dot product. So make sure that you're showing in the dot product that the direction vector for the line, which I did in purple, is perpendicular to the normal vector of the plane. Okay, so when I do the dot product, I get a 0, which means that those two things are perpendicular, which also then means that the line and the plane are parallel to each other. So in this case, proving that they're parallel, I then have either this guy where it's floating above and parallel, or I have this guy where it's floating on top and parallel. Okay, so I got to distinguish between the two, and again, we can do the substitution and figure out what our t value is. And so when I do the substitution of my line into my plane, I see that I get 0t equals to 6. And so remember, there is no such t value that will ever, when multiplied with your 0, give you 6. And so we have no solutions. And that basically means that there's no point of intersection. And if there's no point of intersection, we're talking about this guy. So your answer is going to be that line and plane are parallel and distinct. So we've seen an example of our second case. We've seen an example of our first case. Obviously, the last example is going to be our last case. But I'm kind of jumping the gun and telling you when I should build up your curiosity. Anyways, example number 3, determine the behavior. So what they mean by that is, how do they intersect? Of a line in parametrics, yay, and a plane in scalar, yay. Okay, so plane's going to be orange, line's going to be purple. If it's a full analysis, did I say that weird? If it's a full analysis, let's do the dot product and prove that they're actually parallel to each other first. So we're going to take the direction vector of the line, dot it with the normal of the plane, see if you get a 0, which I do, and that means that they're going to be parallel to each other. So again, that is the case where you have something like this, or this case where you have the line on top. Okay, so we're going to distinguish between the two by subbing in line 1 into plane 2 and taking a look at what our t value is. And so when I do that, I get my t value as anything, because 0 times any number will give me 0. So there are infinite number of solutions for t. That means that there's infinite points of intersection, and then that line 1 and plane 2 are parallel and coincident. So we're talking about this guy right here. All right, so that is, one of our last videos. We're pretty close to the end of Unit 4. That means that we're really close to calculus, which means that we're really close to the middle of this unit, or not this unit, this course. Wow, this course is just flying by. This is so crazy. All right, so thank you for joining me again, and can't wait to see what I have next in store for you. See you later. Have a great day.